Now, earlier on in the chapter, I talked about standardizing a normal distribution into a standardized normal distribution. And what that did was it created the normal distribution shape such that the area under the curve was equal to 1. And now we're going to start looking at the area under the curve and how that relates to probability. And one of the most important rules when it comes to normal distributions is called the empirical rule. Sometimes it's called the 68, 95, 99, 7 rule. And you'll kind of understand why here in a minute. So the important thing to remember about the empirical rule is that it only applies to data that is symmetrically distributed and bell-shaped. So it only applies to normal distributions or standard normal distributions. Right. What the rule says is that between +1 and -1 standard deviations above and below the mean, the area between them, so this area, is equal to 0.6826. Between, let me erase this now, between +2 and -2 standard deviations, this area underneath the curve between +2 and -2 standard deviations is 0.9544. And between +3 and -3 standard deviations, the total area under the curve, doing my best to color in with the brush tool I got, is 0.9972. And remember that with a standardized normal distribution, the total area under the curve is equal to 1. So everything underneath the curve, all the way out this way, all the way out that way, total area is equal to 1. And that's basically what the empirical rule says. The empirical rule and the relationship between the probability of data between standard deviations of the mean is kind of what it relates. Now, there's a couple other percentages, probabilities that are important. So most people will think of a 95% probability, not a 95.44. So what you'll see is that an area of 0.95 or a 95% probability lies between plus and minus 1.960. And 1.960 is just shy of 2, which relates to an area of 95.44%. So 95.44% is between -2 and +2. If you want an area that is exactly 95%, then you need to cut it off here at positive 1.96 and negative 1.96. And this area that you have between those two z-scores will be 0.95 even. Oops, come on, please erase. There we go. And likewise, an area of 99% lies between the z-scores of positive and negative 2.576. All right, so let's kind of look at an example of this. So here we've got a distribution of the weight of adult males in the United States with a mean of 190 and a standard deviation of 10. This is the same as we had previously. Um, and we looked at a random adult male, who weighed 175 pounds. And if that adult male was 175 pounds, what was their z-score? And it came out to negative 1.5. So, if we look at this normal distribution where we've got a mean of 190 with standard deviations of 10. So if we go 10 above 190, we get 200. If we go 10 below 190, we get 180. And a weight of 175, that was a z-score of negative 1.5. So that's kind of where we're sitting here with this picture. Now, what if I wanted to know what's the probability of randomly selecting a person from the population who weighed less than 200 pounds, but more than 180? What is that? Now, knowing that the population of adult male weight is normally distributed, we can look here at 200 and we can look at 180. And you can see here that here's our mean plus 1 standard deviation, here's our mean minus 1 standard deviation. And so the area between plus 1 and minus 1 standard deviations, this area under the curve between those 2 points is 68.26%. So the probability of randomly sampling an adult male in the United States that's between 180 and 200 pounds is 68.26%. Now, what would be the probability of randomly sampling an adult male that's between 210 pounds and 170? Well, 210 is 2 standard deviations above, and 170 is minus 2 standard deviations above. So what's the area under the curve between positive 2 and negative 2 standard deviations? What is this area? Well, according to the empirical rule, it's 0.9544. Or 95.44%. Now, what makes the empirical rule convenient is that often we are only concerned with, plus 1 standard deviation, minus 1 standard deviation. And so we can quickly use these areas here for probabilities. But calculating the area under the curve is typically something that's done in calculus, for example. But this is not a calculus class. But your calculator will be able to calculate the area under the curve using its own calculus. Okay. And we'll be calculating areas under the curve, for some values that are pretty easy to understand and some that we will need the calculator to determine for us. But of course, you'll have to know what it is that you're doing in order to calculate that correctly. All right. So let's go ahead and stop it there with this explanation of the empirical rule. You're going to see this a lot more moving forward, so there'll be more opportunities to learn. And we'll do an example of this here next. All right, let me know if you have any questions.